Are you going to debug the phone?
My name is Christopher Brady.
My name is Loudon Norton.
And my name is Anthony Gott.
And this is the report for our FPGA-based 16 QAM communication system design. We designed both the transmitter and the receiver. This is our Simulink model. As you can see on the left, we have a random symbol generator, which we use MATLAB to generate random 4-bit symbols. We then split them into the in-phase and quadrature components, which we then map to four levels. We then pass that through a square root raised cosine filter. For pulse shaping, this is to both reduce the bandwidth and minimize the intersymbol interference. We also upsample. Here we modulate the symbols by multiplying by sinusoidal carriers. We multiply the in-phase by a cosine carrier and the quadrature by a sine carrier. We then combine those two for transmission. On the receiver side, we split the received signal into the two channels. We then demodulate it by multiplying again by the sinusoidal carriers. If the local carrier frequency is the same, the signal can be easily recovered. In an actual implementation, the carrier frequencies may be slightly different. If this is the case, a carrier correction hardware is needed, such as the phase lock loop. We have not implemented this for our project due to time limits. We then pass it through a matched square root raised cosine filter and downsample. We then output the recovered signal to the scatter plot. As you can see here, this is our scatter plot results. And this is our in-phase and quadrature received and transmitted symbols. Next we'll show you the hardware implementation results. We take our results from our implementation and save them to a text file. We then import that text file into MATLAB to compare with the simulated results. This here is the transmitted I and Q before the modulation and raised cosine filtering. This is our filtered I and Q. The theoretical and the actual results are shown. This is the sine and cosine carriers that we use to modulate our signal. This is the modulated I and Q channels. No noticeable differences can be seen between the MATLAB and the actual VHDL signals here. This is the demodulation sine and cosine. This is the in-phase for the MATLAB on top. The second one is a partial MATLAB, partial VHDL, where we take our VHDL results and we multiply them in MATLAB to obtain the results. And then the bottom one is the VHDL results that we actually obtain. This is both for the in-phase and the quadrature components. Here's the demodulated channel that's on top, and then we resize it for the bottom for both the in-phase and the quadrature. This is the MATLAB matched filter demodulated VHDL signal. Note a few initial zeros are shown on the scatter plot. This is due to some delay. These are the actual results we obtained from the VHDL. Here you can see the in-phase, transmitted, received, and then sampled signals. We obtained those for both the in-phase and the quadrature components. Here we show the transmitted and received in-phase and also quadrature. Here we use a threshold device in order to increase accuracy for our recovery of the symbols. And when we use that, this is our received and transmitted in-phase, and then our received and transmitted quadrature. Next we move over to the actual hardware implementation. This is the results from our D to A converter, and we also have the symbol generator here. And this is all being run directly on the Xilinx board.